Good morning, everybody. Start with some green check marks, please. We'll get started. I said that today, if you guys had some questions regarding the Unit 6 stuff, the types of reactions, we could spend some time going through that. So I'd like to do that for sure. I'll do a few of the examples that were in the learning guide there, maybe. And then moving on to Unit 5. Now Unit 5, again, is really, really small. It's kind of like Unit 6. There's only two sections. There's acids and bases, and then there's kind of another section that's called salts, and we throw organic compounds in there as well. And this Unit 5 it's not a big portion of the course. It's generally pretty small, and the good news is there's a lot of reference to the data book. So Unit 5 is just kind of looking up stuff in your data book, which is nice. You don't have to memorize a lot of stuff. So that's what we would like to do today. I'll start off if anybody has any specific questions on Unit 6 that they wanted to go through. I'd be happy to do anything there. And then if nobody has any real specific questions, maybe I'll just do a couple general questions from the learning guide, and then we'll move on to Unit 5. So if you haven't had an opportunity to get Unit 5 printed, now would be a good time to do that, so it's ready to go. And we'll just get started here. Another thing that I should mention was that because sailing was canceled on Friday, I know at least Connor was there, we've rescheduled sailing till Thursday this week coming up, or sorry, this 2 days from today, Thursday. And if you want to go sailing, that's fine. We won't do a ton in class. I'll do like a little bit of stuff. So if a bunch of people are away sailing, I don't want to go through a bunch of new material. So I want to give you guys an opportunity to go sailing. So if everyone's like, yeah, we're going sailing, then perfect, go sailing. But if only like one or two of you go sailing, then we'll just do a little bit of stuff in class, but not a ton. Basically, probably just wrap up the acid-base unit, so Unit 5.1 and 5.2. Costin, I'm seeing your question, so we'll start with that. Jump over to one note here. All right. So this is 2G. Costin, this is the one you're maybe referring to. G, H, I, J, K, and L. I assume it's 6.1. Maybe I jumped to 6.2. Nope. That is the right one. 2G. All right, so identifying the different types of reactions. We can definitely go through some of these. The idea here is that we take that little table that we had. I kind of summarized everything. So you're trying to figure out what type of reaction is, and the best way to do this is to look at, where the plus signs are, where the arrows are, how many things you're starting with, how many things you're ending with, either elements or compounds. Once you get to wrap your head around what specifically is going on in terms of, elements, compounds, what you're starting with, what you're ending with, you can, place the reaction into one of these 6, and that's what we need to do. So, letter G. I'm starting with 2 things, I'm ending with 2 things. You'll notice that one of the things that I'm starting with is magnesium, it's just Mg. So because this Mg is just hanging out by itself, it hasn't formed a compound with anything. It's not like MgCl or MgO or anything like that. It's just an element by itself. And then I notice on the product side, or on the other side of my arrow here, I have another element by itself. So if I were to go back to my sort of general forms of reactions here, it's kind of looking like a single replacement reaction because I'm starting with a compound and then something by itself, and I'm ending with a compound and something by itself. So, if we look really carefully, we can see that the magnesium is kicking the hydrogen out. The hydrogen's now hanging out by itself, and then the magnesium and the chlorine are forming a bond or a compound. So this is a single replacement reaction because the magnesium's kicking the hydrogen out of the compound that it's in. The hydrogen's now by itself, and then the magnesium's bonded with the chlorine. So that is definitely a single replacement reaction. I think I've done most of these. We did the first page. We did the second page, third page. Is there any other specific questions that anybody had in regards to these types of reactions? Anything you want to go through, anything you're confused about? We also did the reaction rate stuff where we sped up and slowed down the reactions, probably a little bit more straightforward than the types of reactions that we've been looking at. The sheet that you looked at to see which one the question was, I need that. Sheet that you looked at. Like the summary one here, Costin, is that what you're talking about? With all of these different types? Okay, I can leave that up for a second. So yeah, just a summary of all the reaction types. Decomposition, synthesis, single replacement, double replacement, neutralization, and combustion. Remember that the neutralization, combustion are kind of just fancy types of the double replacement reaction. So when we have neutralization reactions or combustion reactions, basically they're just kind of like swapping partners like they're in a double replacement, but they're just kind of special cases. You know, with the neutralization, you have the H and the OH for the acid and the base. Those give us water. And in the double replacement, you just have the A and B switching with the C and D. So it's a similar sort of scenario. Combustion is kind of one that you just have to recognize. You have oxygen on your reactant side, you have carbon dioxide and water being produced. And combustion reactions are always the same. They always produce carbon dioxide and water. So you should be able to identify those fairly quickly. All right, let's move on. If nobody has any further questions on Unit 6, we will say sayonara, Unit 6, and take a step backwards to Unit 5. Unit 5 is a little bit more chemistry, and Unit 7 is technically physics, but it kind of looks like chemistry. And then we just have the 2 physics units left. So we're really in the home stretch here, guys. And for those of you who are kind of maybe falling a little bit behind at this point, just, you know, do your best to get through this chemistry stuff. I know it is a little bit of a slog. It's definitely trickier than the biology unit and even the earth science stuff that we've been doing. So if you can just, you know, work through the chemistry, it's not the whole course. If you can just get some stuff done, you can just keep going, and you shouldn't have any issues completing the course. But the chemistry, unfortunately, because you have Unit 4, 5, 6, and then even 7 looks like chemistry, it seems like the majority of Science 10 is chemistry, when it's kind of chemistry in disguise. So do your best to kind of get what you can in and done and get some marks and write those tests. All right, acids and bases. This is Unit 5. Now, we talked about in the neutralization reaction, I said, you haven't studied any of this stuff yet. Acids and bases, we're going to talk about later in Unit 5, because we kind of did the units out of order, just because I think they fit a little bit better that way. But acids and bases are extremely common things. You have acids and bases in your house. You have acids and bases in your body. You use them every day, although you may not realize it. So acids and bases they can be dangerous if they're concentrated enough. Definitely burn your skin, cause a lot of irritation. And acids especially can eat away at metals, which isn't a good thing if you get some acid on a metal. And as a general rule, it says never try to identify an acid or base by taste or touch. It's kind of funny that we say that, and then we say, oh yeah, by the way, acids are sour and bases are slippery when you touch them. So we tell you not to do it, but then we say, okay, we can classify them based on their taste and touch. So it's just a general rule in science. You don't want to taste or touch something that you don't know what it is. And you could probably extend that right into your homes. If you have some unknown substance, I would say the first thing you probably don't want to do is taste it to figure out what it is. But it seems like common sense, I suppose. All right, acids and bases are measured on the pH scale. And if you recall back to the Richter scale when we were studying earthquakes, Richter scale was a logarithmic scale. So each step on the Richter scale, if you went from 0 to 1, 1 to 2, each step, 1, 2, 3, 4, 5, was an increase in 10 times the strength. And the pH scale is a similar sort of scale. Each step on the pH scale is a 10 times stronger. So if you were comparing something from like a 5 to a 7 in terms of pH, that's 2 steps, means it's 10 times stronger. And one really cool thing about the pH scale is that it's an all-inclusive scale. It has acids and bases right on one scale. So instead of saying, you know, this is the strength of the acid, this is the strength of the base, and having 2 separate scales, we put them on one scale, and that scale goes from 0, which is extremely acidic, through to the middle, which is 7. Right in the middle is neutral, meaning that it's just basically like pure water, distilled water, is neither acidic or basic. And then you keep going all the way to 14, and if you have something that's 14, it's really, really basic, and it can be really corrosive. So each step on the pH scale is kind of like a step on the Richter scale. It's a logarithmic scale. Each step represents a 10 times increase in strength. So what we do to determine if something's an acid or a base, if it's just an unknown, we use something called an indicator. And indicators can change color basically depending on whether they're in the presence of an acid or a base. Now, you know, in sort of everyday life, you're probably not going to have a lot of mystery substances or a lot of indicators kicking around. But if you do pursue chemistry any further than grade 10, a lot of what you do in chemistry revolves around figuring out how acidic or basic something is, and kind of allows you to determine reactivity and whatnot. So the most common indicator is called litmus paper, and I tried to find some in our storage room, but I couldn't for whatever reason. I don't know if we used it all or whatever. I thought there was a ton of it, but I just couldn't find it. So basically it's just tiny little strips of paper, and it's either red or blue. And if you put it in, if you put litmus paper, doesn't matter if it's red or blue litmus paper, if you put it in some base, it turns blue. Think of it, the B in the B is base blue. And then if you put it in something acidic, it turns red. So it could start off as blue paper, you put it in acidic paper, and it turns red. So litmus paper is going to be blue in a base, red in an acid, and if it doesn't change colors, then it's neither in an acid or a base. You can use something called a universal indicator, and a universal indicator will tell you the general pH of something. Does anybody have a hot tub or a pool at home? if you have a hot tub or a pool, does anybody have a hot tub or a pool? Somebody's got to have a hot tub or a pool. There you go. So maybe you've done this before, or maybe you've seen your parents do it, but you take either a little scoop of water from your pool and then you add a couple drops and you shake it and you compare the colors. Or at home I have a hot tub and we have these strips of paper and you dip the paper in the water and then you compare the color of the paper to the chart on the side of the bottle. Has anyone done that before with a pool or a hot tub? Figure out how much kind of chemicals you have in there. It's really common to figure out the pH of your pool. You want to have a little bit of pH in your pool to keep the chlorine level stable and things like that. So, okay, so you guys have used indicators before. If you haven't ever seen that before, we're going to do a couple here today, so you'll have a general idea of what it looks like. You can use a pH meter. It just basically tells you how conductive the substance is. The more electricity it conducts, basically tells you how acidic something is. Indicators change color at different pH values. And we'll use something called bromothymol blue. I think I have some bromothymol blue right here. Bromothymol blue is actually brown, which is kind of strange. And bromothymol blue changes colors in the 6 to 7.6 range of your pH scale. And then there's something called phenolphthalein. And if we're in a classroom, I make everyone say phenolphthalein because it looks so funny. So this is what phenolphthalein is. It's this it's a clear liquid. This one has a little bit of powder in the bottom, just kind of came out of a solution. But phenolphthalein is really cool because it turns this really bright pink color, and that we'll look at in a second on our chart. So we have a couple indicators there. And then you can have natural indicators. If you take cabbage, really weird, and then you I think if you boil it and then you take the juice of the cabbage that was boiled, it'll change color depending on if it's an acid or a base. So it's a natural indicator. So this is the chart that you guys have in your data booklet. It's in color here, which is fairly important. This is on page 3. And the chart tells you what colors various indicators will be. So in the very middle, we kind of have the scale from 0 way over on the side. You have something that's highly acidic at 0, and then you go 1, 2, 3, 4, 5, 6 is that milk, 7's neutral, which is just pure distilled water, and then 8, 9, 10, 11, 12, 13, 14. So up at the top, you have sort of common items that are going to be either acidic or basic. So the first one at 1 there is your stomach. Your stomach has hydrochloric acid in an HCl, and hydrochloric acid is a very strong acid at a pH of 1. There are stronger acids, but it's fairly strong. And then a lemon, like lemon juice, is a pH of 2, so lemon juice is highly acidic. Grape juice or grapes are acidic at a 3. Then you're getting less acidic down to tomato at 4. Bananas, who knew? Slightly acidic at a 5. Milk is slightly acidic at a 6, and then you have kind of neutral. And then basic, you'll notice that most of the things that are kind of common that have bases in them are cleaning products like ammonia, bleach, oven cleaner. These are very, very basic things. And when we say even like soap is a 10 on the pH scale, you imagine that soap is very slippery. Same with ammonia, bleach, oven cleaner. These things are very slippery, and bases are slippery, which makes them good cleaners because they can, take off stuff that's kind of stuck on there. If you're cleaning, down at the bottom you have all your indicators. So methyl orange, methyl red, bromothymol blue, litmus paper, phenolphthalein, and indigo carmine. These are kind of the most common indicators. So how we use this chart is you find the thing that you want to look up the pH of, and then you can see what color it changes depending on where it falls on the chart. So let's look at sort of the definitions. Maybe we'll just jump over and we'll look at some of the indicators here. So I have step across. I have just 2 empty beakers here. And then, as I said before, I have something called bromethymol blue, and I have phenolphthalein. And these are going to change colors depending on whether they're in an acid or a base. Now, I raided the science supply closet here, and I found some unknowns. So you can see this thing just says A on it. No idea what that is. Letter E. So this is part of an old lab, I think. And I have no idea what these are. Literally, they've been in their closet for a long, long time. So I really just have absolutely no idea. So let's just take one and we'll try to figure out if it's an acid or a base. The C is kind of a clear liquid. So I'll just put a few drops of it in the bottom of each of these beakers. There we go. And again, it's just a clear liquid down there. So if you have your data booklet out, you should be able to figure out what color this is changing. So that's C. Let's leave that out so we don't mix it up. So I'm going to use bromethymol blue. And bromethymol blue, on the chart, I just have it next to me so I can see it here, but bromethymol blue in an acid is going to be yellow, and in a base it's going to be blue. So it starts off as this like really brown color. And if I take this, and again, I don't know what C is. It could be an acid, could be a base. Maybe it's nothing. Maybe it's just completely neutral. But if I take the bromethymol blue and I put a couple drops in here, you can see that the bromethymol blue started off as this kind of brown color, and it's kind of yellow in this bottom of the beaker. So if it's yellow, it's a good chance that whatever this is, letter C, is an acid, just because the bromethymol blue changed to that kind of yellowish color. Now, maybe you're just thinking, oh, Mr. Borden, you've just diluted whatever was in here. So if I put it in here, we'll see what color it changes, if any. So again, it's still kind of that yellow color. So it's a good chance that good old letter C here is an acid, just because it's that bromethymol blue turns yellow in it. Let's see if I can find a base. I have a base here. This one's labeled base. So just so we can compare it to see what color bromethymol blue changes to when it's in the presence of a base. So again, just a clear liquid, but I know it's a base just because it says base. This bromethymol blue, because it's bromethymol blue, and this is why it's called bromethymol blue, should change to a nice blue color. And you can see that instead of being that kind of yellowish color, this is what it looks like in an acid, and you get this really, really vivid blue color in a base. So that's color bromethymol blue is on the spectrum. So you have on your sheet, you know, a base is this blue color. It started off as this kind of really brown color. And then you end up with this kind of yellowish color. The one that I like the best is phenolphthalein. So I'm going to take some base again, just because I know it's a base. I'll put a few drops of it in here. I don't know what it is. It's probably calcium hydroxide or something like that. So phenolphthalein starts off as a clear liquid. This one has a little bit that came out of solution, so it has this white powder at the bottom. But in a base, if I look at the indicator sheet, phenolphthalein should be a really pink color in a base, and everything else should be kind of clear and colorless. So this one is very obvious when you put, again, just like the blue changed to that really bright blue color, I take two completely clear liquids and I mix them together, and I get this really bright pink color. And that is, again, I took a base, which was completely clear, and then this phenolphthalein, which was this clear liquid, and I mix them together and I get this kind of really bright pink stuff. And that's how indicators work. They change colors very quickly. Let's do one more unknown. If I have enough beakers here, see if we can figure out what it is. So So I did C already. Letter E here. I don't know what it is. It's an unknown, and it is a clear liquid. Does anybody have a preference to indicator we should use? Which one you like the color of the best? Oh, that wasn't good. I'm always making a mess of the studio. All right, letter E. I'll put a couple drops of phenolphthalein in here to see what it was. See how urgently I need to wipe it off my body. So it's definitely a base. You can see that it doesn't change color, so it's a fairly weak base, but that phenolphthalein's that nice pink color. All right, so there you go. That's how indicators work. Now that I'm covered in a mystery base, I'm going to go wash my hands. I'll just throw up the next slide here and you guys can read about some acids. I'm going to wash my hands and I'll be back. All right, welcome back. Bases are good cleaners, so the good news is when I clean up the huge mess that I've made in here, the studio is going to be nice and clean. Mr. Rosso really appreciate it, I'm sure. So that's how indicators work, and most of the questions you're going to see associated with indicators will say some unknown solution turns phenolphthalein pink, and it might give you some like combination of indicators. So it'll say like it turned phenolphthalein pink, but I don't know, but indigo carmine was blue still. So if that was the case, if it's pink and blue, you kind of need to look where they overlap, where phenolphthaleine's pink and indigo carmine might be blue. So you're looking at a pH of either 10 or 11 in there. They also have these kind of transition periods where phenolphthalein will start to turn pink around about an 8 and a bit, and then it won't finish turning pink until it gets to a 10. So it just kind of depends on the question. They'll always, it doesn't just turn pink instantly. It's kind of a bit of a combination of things. So there you have it. Just thinking I can, maybe if we have time at the end, I can show you one more thing. So acids. Acids often behave like acids only when dissolved in water. So generally speaking, acids are going to be in water. or a liquid solution of sorts. And that AQ, so we had solid S, liquid L, G gas for our reactants. If we have reactants or products with those little brackets at the end of them, if you see AQ, aqueous, just means dissolved in water. So typically speaking, acids are going to start with an H. So HCl is hydrochloric acid, HNO3 is nitric acid. The one exception you'll see is when you have carbon in there. And CH3COOH is acetic acid. And acetic acid you guys have in your house, it's very common. Does anybody know what acetic acid is? Its common name? I was actually using some acetic acid the other day, and I forget what we were cooking. Tylenol isn't acetic acid. That's acetylsalicylic acid, which is ASA or aspirin, I believe. I always get them confused. Ibuprofen, aspirin, and Tylenol. ASA, acetylsalicylic acid. I believe that's aspirin. Anybody can check. Acetic acid. Did I get a thumbs up? Yeah, ASA is aspirin. Okay. So acetic acid is actually vinegar. And we were cooking something, and my wife said, "You want to grab the rice wine vinegar out of the fridge?" So I pulled it out, and right on the label it says acetic acid 0.003% or something. So if you have vinegar in your house, if you're interested, maybe later browse in the pantry for a snack, just grab your vinegar and see if it says acetic acid, and it'll usually tell you the concentration right on the side of the bottle. The stuff you have at home, acetic acid, in terms of vinegar, the stuff that you're going to actually eat and consume, it's not very concentrated, but you can, get more concentrated versions of the same stuff. So these are the rules for naming acids, and I, in the past, have spent a lot of time making sure students have a good, grasp and understanding of how to name acids. And then as I kind of realized that there's very sort of few questions regarding naming acids, either on the provincial exam, as we used to have, or kind of moving forward, there isn't a huge, push to name acids. What I will tell you is this. In your data booklet, on your polyatomic ion sheet, if I can find the right page here, data page 5, in the top corner, next to the polyatomic ions, above your prefixes, in the top corner you have some names for common acids. So HCl, hydrochloric acid, H2SO4, sulfuric acid, HNO3, nitric acid, and HCH3COO is acetic acid, so they've written it with the H first. So you have these common acids here. When you are asked to name an acid, if you are asked to name an acid, go to that sheet and think of the names that are there and see if you can kind of follow the rules. So if you have hydrogen and just a non-metal like chlorine, fluorine, bromine, just hydrogen and regular old non-metal, it's hydrochloric acid or hydrofluoric acid. So what you do is you change the "ide." If you had HF, you would normally call that hydrogen fluoride. Instead of calling it hydrogen fluoride, you're going to call it hydrofluoric acid. So you start with the hydro, you change the ending to "ic," and then acid. So HF is hydrofluoric acid, HCl is hydrochloric acid, HBr is hydrobromic acid. What's another one? HI is hydroiodic acid. Sounds funny, but it's the way it goes. And that is what happens if you have H and then just a non-metal. So that's the first sort of thing you can get. The second one you can run into is if you have something like hydrogen carbonate, instead of calling it hydrogen carbonate, it's carbonic acid. So you change the ending to "ic" and then acid. The difference between your eights change to "ics," but you don't start the hydro. So if you had HF, that's hydrofluoric acid, whereas you have something like HCO3, because it would normally be called hydrogen carbonate, the carbonate changes to an "ic," and then you add the acid on the end. And then if you have an use, so hydrogen sulfite, like SO3, would normally be called hydrogen sulfite. You'll call it sulfurous acid. So these are the three scenarios you can run into. Your ides change to hydroic acids, your ates change to ic acids, and your ites change to ous acids anytime you start with an H. So if you have a substance compound that begins with an H, it's going to have an acidic name or a special name for its acid. So there you go. Those are the three rules for naming acids. Ides change to hydrofluoric acids, ates are ic acids, and ites are ous. Bases. Bases end in OH, always, always, always. And the good news for bases is they don't have fancy names. It's just always NaOH, sodium hydroxide, MgOH, magnesium hydroxide, CaOH, calcium hydroxide. So OH is on your polyatomic ion sheet. There's no special names here. There's nothing necessarily too special about your bases. Generally speaking, we dissolve bases in water, and you'll see the little subscript AQ next to them. Common bases, sodium hydroxide is used in a lot of cleaners. Magnesium hydroxide is used in cleaners. That's probably what I spilt all over myself here before, something like probably sodium or magnesium hydroxide. Calcium hydroxide, you'll see that in kind of like antacids and magnesium hydroxide. So if you've ever eaten like Tums or any of those kind of chewy antacids, they're usually calcium or magnesium hydroxide. Ammonium hydroxide is kind of like an oven cleaner type deal, strong cleaner. They don't have special names, just the metal and then the hydroxide like you'd normally name everything. So there's nothing really special in terms of the bases. The acids are the only ones that have the special names. So acids and bases are going to conduct electricity when they're dissolved in water. Basically, anytime you take an ionic compound and you dissolve it in water, it doesn't stay as the compound. It breaks down into the two parts. So acids and bases are no exception to that. Essentially, you can't have an H and an OH mixed together. And what do I mean by that? Let's see if I can go back over here. I'm going to just try one thing. Mr. Ross can maybe just switch the old camera back. So we had this base that turned this nice pink color because it was basic. Now, letter C was an acid. So if I have a base, and this is base, and it's this pink color, and then the C we tested, and I believe we found the C was an acid. Pretty sure. So basically, if I mix an acid and a base together, they neutralize. We've done neutralization type reactions. So eventually this should change to water. And you can see that the pink color just vanishes. Once I get enough acid in there, it eventually becomes water. Now it's acidic. Now, if I don't really have any left, I can change it back again. If I have a base now, if I'm adding a bunch of extra OHs in here, eventually the indicator's in there, right? It should change back to a pink color. So just a few drops at a time. I'm going to just mix it up a little bit. So I'm adding OH, I'm adding OH, I'm adding OH, and eventually the solution here is going to get to the pH where phenolphthalein changes back to that really bright pink color. And if you ever pursue chemistry any further than, well, you might do it in Chemistry 12, you do something called acid-base titrations where you add slowly, one drop at a time, an acid or a base until your indicator changes color, and that way you can figure out the concentration based on how much acid or base you added. So eventually this should start changing to a pink color. It is a little bit when the drops hit there, changing to a pink. Might have to add a lot. Trying not to explode the top off my dropper again. Come on. The acid was just a lot stronger than the base, so I guess it's still working its way. Might speed this whole process up just a little bit. Instead of a drop at a time, we'll add a lot. So you can start to see it changing to that pinkish color. So there's a little bit of acid in there. I'm adding more OH, adding more OH. I'm going to add all of this. Might have to mix some up later. Well, unfortunately, I ran out of base. I don't think I have any more base left. A little bit of E left here. Let's see if I can completely, no, just not enough base. So eventually it would change back to that pink phenolphthalein color. Unfortunately, I ran out. So there we go. We can change the indicators back and forth. If the indicator is present, you can change it back and forth, and it'll go from, it'll change through the color. So I can go from pink, and then I can add some acid, and it'll go back to the clear again. So the amount of H and OH, eventually they'll kind of balance out in the middle, and you have something that's completely neutral or water. If I add a little more base, the OH goes up, the H disappears. So you can't have H and OH at the same time because the H and the OH together produces just water. And this chart is also on the acid-base table. It's kind of across the back. And if you have a bunch of hydrogen ions in there, it's going to be acidic. If the hydrogen slowly disappears, you get a bunch of OH ions in there, it becomes basic. And you just go back and forth. And if they're completely balanced, you're right in the middle, it's just pure water. You add a little more H, you kind of go off to one side. You add OH, it goes off to the other side. So these are the general properties of acids and bases. And they are just kind of, essentially just a summary of all the things. So acids, again, we don't ever want to taste anything, but acids are sour. So you've eaten things that are acidic before, like a lemon is highly acidic. That's why it's really sour. Vinegar, very acidic. If you were to just drink pure vinegar or taste it, it's kind of sour. Bases taste bitter, and they're generally toxic. They're not good for you. You don't want them to taste them. Touch. Acids will burn your skin. They'll kind of eat away at your skin. Bases will do the same thing, but bases feel really slippery. And to think about a common base would be something like soap. Why is soap slippery? Why do we use a base to clean our hands? Because that base is good at getting dirt and whatnot. Because it's so slippery, it can pull the dirt off your hands and skin. And that's why we use soap, which is basic to clean things. Indicator tests. It doesn't matter what you have in terms of litmus paper, but acid is going to always turn litmus paper red. It doesn't matter if you're using blue litmus paper or red litmus paper, it's going to turn red, as a base will turn litmus paper blue. Acids corrode metals, we'll eat it right away at them, and bases won't do anything. Both acids and bases will conduct electricity. pH, acids are less than 7. Bases are more than 7. And acids produce hydrogen, bases produce hydroxide. So that's acids and bases in a nutshell. Anybody have any questions on acids and bases? Anything I didn't touch on? Anything you're unsure of, confused by, want clarification on? Negative. All right. Time is it? It's 10:20. So let's maybe take a peek at the learning guide and see what's there in terms of questions on acids and bases. So this is the Unit 5 learning guide. We've gone through the acids and bases notes. There wasn't a ton of stuff there. Bases, looked at the table. You guys have the table. And just some basic questions on acids and bases. So there are 9 questions. Naming acids might be a little tricky. We'll spend some time on that. And then bases naming. All right, so you have about 15 questions on acids and bases. And then we have salts and organics. I tell you what, let's give you guys some time to work on the acids and bases practice, and then I'll come back and answer any questions you have, and then maybe we'll just leave it there for today, and we'll cover the second section on organics and salts next day. The organics and salts section's really, really tiny, and there's not a lot of stuff there, so nothing terribly difficult to worry about. Maybe we'll throw up 20 minutes, and you guys can spend some of that time going through the questions on acids and bases. And then we'll come back, and if you have some questions, especially on the naming, because that can get tricky, I'll go through some of those. So we'll put up 20 minutes. I'll meet you back, and we can go through what all of this is about. Good luck. We'll see you back in 20. Maybe. So it's about 10:15 now. 10:15 plus 20 minutes would be 10:35. See you guys at 10:35. All right, guys, welcome back. I'm going to start with just a green check just to make sure everything's working. Thanks. Did you figure out AQ, Costin? Did you sort that out? Hopefully. Perfect. All right, were there any questions, kind of specific, not specifically? I wanted, what do you mean, yeah, sorry, no? I want to do the naming stuff with you guys, so we'll do that together, but 6 or 8, perfect. That's a good start. Okay. What does it mean when you see AQ? AQ. Means aqueous, which is dissolved in water. So if you had something like HCl, in terms of a chemical reaction or a chemical equation, if I had HCl, sometimes you see the little brackets like AQ plus, I don't know, let's pick a metal, silver. As a solid, produces hydrogen gas, and what else would it produce? Silver chloride. So when we do chemical equations, when we have our states of matter, the solid, liquid, gas are, so if I had like a pure substance, so imagine just like pure silver. That's just a metal. You could have it solid, and something like pure hydrogen. If hydrogen gas was released. But if you take something and dissolve it in water, not only do you have that chemical, so the hydrochloric acid, but it's also dissolved in water. So there's water there, but the water is not taking part in the reaction. So it's just saying, hey guys, there's some water here. It's not part of anything, not part of the reaction itself, but know that the hydrochloric acid is dissolved in water. So that's what that means. What's different about the positions of that letter if an acid starts with C? So if you have an acid, it always starts with H, but something like acetic acid or vinegar, a CH3COOH, is acid, but because it starts with, because it contains carbon, it's going to not have the H to begin with. You can also write acetic acid as, I'm going to make sure I get this right. It's on this data booklet, HC. This isn't as common, but this is how you have it in your data booklet, CH3COO. So that is acetic acid, just written differently with the H first. So they're both the same thing. They're both acetic acid. They're just written 2 different ways. So sometimes you'll see it with the H first, sometimes the H comes at the end. Generally speaking though, acids that contain carbon will have the carbon written first. So that's kind of the rule as opposed to the exception to the rule. Kyla, does that help you out with those 2? Perfect. All right. What's 5? It's a number. Comes after 4, before 6. Litmus paper, Costin, is the most common indicator. It's inexpensive, cheap, and it's the easiest way to test for an acid or a base. All right, let's, and it doesn't change color. So here's kind of the thing with litmus paper. Let's say I had a piece of blue litmus paper, and it just looks literally like this, and it's just kind of blue. There we go. There's my blue litmus paper. If I put my blue litmus paper in a jar that contained some substance, and if this was just something like water, the blue litmus paper would stay blue. It wouldn't change color. if I took blue litmus paper and put it in something like a base, something like, let's say, sodium hydroxide, the litmus paper is going to stay blue. It's not going to change color. But if I took red litmus paper and I stuck it in a base, like sodium hydroxide, the red litmus paper, the bottom part that was in the sodium hydroxide, would change to a blue color. So that's how litmus paper works. But litmus paper doesn't know if something's neutral. So I can't tell if something's an acid or a base if it doesn't change color. So if litmus paper doesn't change color, it could be neutral. But if litmus paper changes color, you know for sure that it's an acid if it's changing to red, or a base if it's changing to blue. And the complete opposite's true for if I put this in an acid. If I put this in an acid, the blue litmus paper would turn red and the red litmus paper would stay red. If that makes any sense at all. All right, I'm just going to jump back to the notes and make sure we get our acids and bases sorted for naming acids, because this can get tricky. So again, the 3 rules. Rule number 1, if we have an "-ide" ending, so hydrogen fluoride, hydrogen chloride, we don't call it hydrogen chloride, we call it hydrochloric, and then we tag an acid onto the end. So that's the kind of the rule there. If we have an 8, so if our polyatomic ion ends in 8, we go "-ous" acid, or "-ic" acid, sorry, and then "-ites" or "-ous" acids. So let's just maybe write these down. 8s are "-ics", 'ites are "-ous's". So if it ends in 8, I change it to "-ic" acid, and it ends in "-ite", I change it to "-ous" acid. And if it's an "-ide", it changes to hydro something "-ic" acid. All right, let's take our rules for a little spin here. So HBr. So I don't know if that's a gross question at all, Leeds. Saliva, I would believe it's acidic, but I don't know that for sure. Yeah, I would guess that it's acidic, Leeds. I don't know why I'm guessing that. Maybe it's not. Just because we're dealing with substance doesn't mean it has to be acidic or basic. Lots of things are just neutral. Yeah, I don't know why I would just assume that. It's a completely unfounded guess. All right, so HBr would normally be called hydrogen bromide, if I name that according to the rules that I normally would use. Now, because I see it starts with an H, I can identify this as an acid. And acids have special rules. So if I am ending in an "-ide", I'm going to use this rule down here. And that rule says that I start with hydro, and then I have bro. Instead of "-mide", I have "-ic", and then acid. So hydrobromic acid. All right, so the next one is just a metal and nonmetal. Again, this would be the same as the one, hydrogen sulfide. I would name it the exact same way. Hydrosulfic acid. my crack team of researchers here in the studio with me have identified for leads the pH of saliva slightly acidic between a 5.7, that's pretty acidic, and a 7. So if I just, let's just go back and look at our little chart here. So the most acidic your saliva can be is around 5 on the pH scale. So if I look here, your saliva could be, you know, somewhere between a banana and milk in terms of acidity. There you go, leads. So slightly acidic, but not terribly acidic. Something like grapes, lemons, you know, are 2 steps on the table away. So you're looking at about, a grape would be about 100 times as acidic as your saliva. Interesting. I don't know why I would have guessed it's acidic. Maybe because your teeth break down over time, but that's kind of more associated with food. I don't know. Shot in the dark. There you go. So the second one, hydrosulfic acid, because we just had, normally it'd be called hydrogen sulfide. Now, this NO2 group, if we were going to name this, we have hydrogen. If I look on my periodic table data booklet, the page with the polyatomic ions, the NO2 group is called nitrite. So this would normally be called hydrogen nitrite. And because it's normally called nitrite, the ending ends in this ite. So instead of using these rules, I need to go to my ite rules. And my ite rules say that I need to change the ending from nitrite to ous acid. So this is going to be nitrous. And what's important to note here is that we don't start with the hydro. We only start with the hydro if it's just a metal and a non-metal. But because we have a polyatomic here, we have nitrous acid. This next one's similar. It would be normally called hydrogen nitrate. And because the ending is normally ate, I would use these rules. 8 goes to ic acid, so this would be nitric acid. And again, because I don't just have a metal-non-metal combo, I have a polyatomic in there, I would lose the hydro. I will help you guys do the last 3, but I want you guys to have a go at them. So I will name the group. So ClO4, I can find it on my polyatomic ion sheet. ClO4 is called perchlorate. Doesn't really look like a perchlorate. CO3 is carbonate. And that last one is acetate. So see if you can name those last 3. They're all 8s. Hydrogen perchlorate, hydrogen carbonate, hydrogen acetate. All right, so there you go. When we have those three last ones are eights, we change the endings to ic acid, and ic acid. So perchloric acid, carbonic acid, and acetic acid are those last ones. And again, acetic acid is one of the common ones that's on your page 5 of your data booklet. Now, I'm not entirely sure how far you guys dug into this. Name the following bases. The base naming doesn't change. If it ends in OH, it's potassium hydroxide, aluminum hydroxide, ammonium hydroxide. So those are named just like they normally would be. And some additional questions, and number 15 is just kind of a summary. That takes us to salts and organics, which we'll cover next day. Before we go, does anybody have any questions they'd like to go through before I leave you? Hopefully you guys can finish off those questions for next day. And hopefully you can also polish off that Unit 6, get it submitted, so we can keep moseying on. Yeah, we'll do acids, bases, we'll do salts and organics next day. That's kind of the last little bit of Unit 5 here. And then that'll be it for Unit 5. Then we have Unit 7, 8, 9. 3 units left after this guy. And essentially, at the kind of the rate we're going, we'll probably have a week-ish, maybe 2 weeks of, a week and a half of review before the final exam. And the final exam will look kind of like the midterm, just mainly multiple choice. I might even pick just an old provincial exam that I have laying around, and I might make my job a little bit easier. I might also kind of focus the final exam mainly towards the second half of the course. I haven't decided which way I'm going to go yet. When's the last day of school? We have school right up until the bitter end here, Costin, and I think Mrs. Wood put the dates on the homepage. Let's have a look. I know the final exams are on here. So, final exam, Friday, June 16th, last day to submit. Looking at this stuff in the middle here. Wednesday, June 21st is your socials exam here at 9, and then the next day, the 22nd. So June 22nd will be the final exam. The 16th is the last day to submit stuff. That last week will be here's a calendar. That last week will be, so your 16th is the last day to submit something, and then you have the 22nd, 23rd are final exams a week later. So there you have it. Last day of class will be on the 23rd. And then you're free. You're free, Costin, for summer. Very exciting. All right, I'm going to leave you guys there. We'll start next day with any acid-base questions you guys might have, and then we will move on to salts and organics, which is just really tiny, quick sections. So last day, I think we have class scheduled for the 2 hours again, but it definitely will not take that long. So plan for about an hour, hour and a half max, depending on how many questions you have next day. And that'll be it for Unit 5. So if nobody has any questions, we will sign off. And a reminder, if you guys want to go sailing, if everyone's like, Mr. Board, I'm going sailing on Thursday, then, if nobody shows up here and everyone's sailing, then, we won't really go through much at all. But if only, 1 or 2 of you go sailing, then we'll just kind of plug away. And of course, it's recorded, so you can just watch it later. All right, guys, have an awesome afternoon. Enjoy the sunshine today. It's supposed to be a nice one. Get outside, go for a walk, and we will see you in class on Thursday. Thanks.